Okay, so if you haven't noticed, your next homework is up on Western Online, has been there since Thursday. So, and I set the due date to be this Thursday, but I'm willing to extend it till next Tuesday. So just take a look at it. We will cover most of what you need today, and so you should be able to start making sense of it. Even otherwise, I think you can probably handle it without all the help from me, but let's take a look at it. So I'm not going to look at the homework directly, but what we want to do is take a look at our plan for today, which will cover essentially we're continuing still with the mathematical preliminaries. And I think till we will still need to discuss a few topics on Thursday. So today and Thursday, we will still be dealing with some mathematical basics. And which is, for some of you, it may just be the review, but that's how it's going to be. And I'm going to keep it this way. Okay, so last time we looked at the usefulness of the Levi-Civita symbol to simplify vector identities. We're going to take that idea further and see how it applies to the situation where you are trying to evaluate vector quantities in curvilinear coordinates. And it turns out those vector identities, you need to be very careful when you apply them outside of the Cartesian coordinate system. So let's take a look at one example because this one is especially interesting and it brings up the issues. So this is one of the examples from the book. I will not be going through all the solved examples from the book. That is something that you have to read. So let me just add maybe a small reading assignment here for you. And the reading assignment is examples 1.1 and 1.2. So they're very straightforward, basically application of the Levi-Civita symbol, Einstein summation convention, the Kronecker delta, all of those to the vector identity evaluation. So let's take a look at now del cross A. So it's a double vector identity, two gradient operators applied to A through the cross product. And we of course know, so we have to prove that this is going to be del dot A minus del square A, right? So we haven't proved, that's just how it looks like. We have to prove it and look at the implications of it if A was expressed initially as a vector in the not in the Cartesian coordinate system, but let's say in the spherical coordinate system. So let's take a look at the ith component. So right now we are still looking at the Cartesian components. So okay, and so then you know how to handle the double cross product, right? So if anybody wants to read out to me how this would look like without looking into the book, of course. And those of you who don't have your faces, you need to show your faces. That's going to be something I'm going to be insisting on this semester. Okay, very good. So anybody, how would we write this down? I want the ith component, so you need to decompose it, write it basically. Think of the triple product as a vector product or the cross product of two vectors. I'm going to split them like this for now. That's the easiest split. So what would be the first term? Anybody?
The levity with the
Right,
IJK.
epsilon ijk, very good.
Then the del
Okay,
del J
del j,
and del cross A K.
a, k. Okay, very good. Thank you, Malik. So everybody agrees with that, right? Now we need to simplify this part. And so that's going to give you another epsilon. So I, j, k, del j, epsilon k, p, q, let's say del p, a, q. Everybody with me so far? Okay, and then because these are now just symbols, they're not vectors anymore, so we can, they commute, so we can move them around. Epsilon I. And by the way, commutation property, even though this is not quantum mechanics, we're just looking at mathematics, but we are dealing with tensors. Anytime you encounter tensors, you need to worry about commutation, because any random matrix or a higher rank tensor like epsilon ijk, it's not guaranteed that the tensors themselves will commute, right? And so you have to, when you have specific elements from that tensor, those are now simple real numbers. In this case, real numbers, there are situations where you may have complex quantities as individual entities, but whether real numbers or complex numbers, they commute. So we don't have any issues there. So what I'm going to do is skip a step, bring these together, this and that, and also do the even permutation of the ijk symbol so that the first symbol is the same. So it will be epsilon kij, and then write down the delta identity. So I'm just going to jump through several hoops here and directly write down delta j, no, sorry, that would be delta I p delta j q minus delta I q delta j p. Everybody with me so far? You understand where that came from? And then the rest of the stuff is the del j, del p, aq. Remember, there is a difference in this delta and this, right? This delta is just the Kronecker delta, and then this other symbol is del. That's how you pronounce it. So make sure you also know how to pronounce these things. Okay, so now somebody has to help me again, and not Malik, somebody else. How do I simplify this? What are the general rules of thumb that I shared with you the other day? So I want somebody to read out to me what this term would give. So I will have the first del, the second del, and the A, but what should be the indices that survive after you have used the Einstein summation convention? Remember, any index that repeats has to be summed over. And so, and then because of the
J.
Kronecker deltas, yes.
Is it J, then I, then J?
J,
Delta J.
okay, very good. That's good. P, I, okay, very good. And then J, okay, very good. So this is trivial. How did you get this one? And how did you get that one? So just explain to us, what your thought process was.
Delta J is the last one. Sorry, del J, which is the last terms. And then
Okay, so let me help you here a little bit. The answer you got is correct, but it's not important to get the answer correct. It's important to know how to get there, because when you know how to get there, you can always do it, right? So let's just do a little additional step here. So I'm going to spell out what the first term looks like, and then spell out the second term. Sorry, I made a mistake. That should be a delta, not a del. Then del J, a P, a Q. Let me use a different color here. So which indices are being repeated? P, right, is being repeated. Q is being repeated, and J is being repeated. So all of those indices are getting summed over, right? But because you have the Kronecker delta survives only if I and P are exactly the same. They have the same value, and J and Q have the same value. What does that mean? If they have same value, that means I don't have to have two indices. I can replace them with one single index. Does that make sense? That's the idea. So, and we choose, just to keep things simple for ourselves, we choose to keep the first index and get rid of the second one. And get rid, I mean, just replace it with the first index, right? Because that's when delta IP would be non-zero. So if I want to remove that delta IP completely, that means in the rest of the physically important terms, I and P should be exactly the same. So wherever I find P, I'm going to replace it with I, right? So I get del J, del P is now replaced with I. That's why you get that I. And then for the second Kronecker delta JQ, that delta JQ, that means J and Q need to be identical, right? And so I'm going to replace anywhere I see Q, I'm going to replace it with J. And so when I do that, right, so actually, strictly speaking, what happens is you get delta I, delta J, right? Del J, del I, A, J, right? And these are now simple numbers, so they are going to be 1. So we can ignore them. And so just move them here. Okay, everybody with me? Okay. And then the second term, now somebody needs to read the second term to me. You understand the thinking process here. So what are the indices that would survive?
It will be AI.
AI. Which AI? This one? This one is not going to be AI. This one would be AI, because you're replacing Q with I from the first one. Q becomes I, and here P becomes J. So that should be like that. Everybody with me? Makes sense? Okay. So we need to be careful with this, but once you get the hang of it, it's not really tricky. It's just, these are just tricks. And what we have here is just 2 terms. Now we need to identify those terms. Again, remember, J is being repeated. So a repeated index has to be summed over in both of those. And the way they appear is going to be crucial. And so you could take this and put it here. Again, that's the commutation of the linear differential operators. The order doesn't matter. If you take derivative with respect to I coordinate first and then with the J coordinate, or other way around, doesn't matter. So I'm going to push this here, provided the AJ always is left to the on the rightmost side there. And so these, where the repeated indices are essentially products. So you get delta I. Sum over del J AJ is the divergence of A, right? So everybody with me? And then the other term, del J AJ, that is so did I make a mistake there? Yeah, I made a mistake there. Sorry. So let me go back to here. There's only one A, so I don't know how you guys did not catch it. There should not have been this first A. This is del, and that is del. Okay, so it's the derivative applied twice on A. A appears only once. And so this is del J. Del J is essentially del squared, right? It's the del operator dot product with itself, which is del squared AI. And I has to be the hanging index because we started with I on the left hand side. Okay, so that's trivial, very simple. And then what we do is identify the whole vector by removing the I, and then this becomes a vector del or the gradient, the del operator applied to a scalar quantity, which is okay, right? That's reasonable, minus del square of a vector A, right? And so all of these things are straightforward. Now, of course, let's take a look at this. This is a non-trivial jump. And so I'm going to just take a look at that. How is it that, this is easy because it's now a component of a vector that's just being multiplied by a scalar, right? And so if you convert that into a vector identity, you know that you would just had three different terms. So for example, delta I del dotted with A, if you are looking at all of the terms here, the full vector of it, okay, that part is simple. This is going to have components, sum over I. I'm going to write it like this. Sum over I, right? E I, the unit vectors, times del I, right? Because it's just now a simple sum over I with EI being multiplied by each term. This part is easy. That's trivial. Okay, that's why the first term can be taken from its component form to the vector form, but that's not so easy for the second one. So we have to literally prove it that actually works, right? So del square applied to A, we want to show that it can be written down as summation over I, EI, del squared AI. Is this true? We're not sure, right? We need to check because there is no guarantee, because the AI is not a vector component by itself. It is actually getting differentiated, right? So after differentiation, you don't know always that the linearity will survive, right? We of course we know the linearity survives, but this is a special case which is true only in the Cartesian coordinate system, and you will see why it's not true in the other coordinate system. So let's take a look at del square A. Anybody has any questions? You understand the case I'm trying to make? This is tricky. And why it's tricky, right? You can't just jump directly. Something that's a component of a vector being operated on del square, there is no guarantee that del square AI, when you add all the components of AI, it would be del square, the whole vector A, right? That's what I'm saying. So let's take a look at this. Let's expand it out. Del squared, and then we say E1. E1 here, I'm veering away a little bit from the textbook notation just because of the other argument that I made. I can combine the two arguments there. Okay, so is everybody with me so far? That's what this del square applied to vector A means, right? And so let's now take it and apply the del square operator individually. And because, okay, in the Cartesian coordinate system, and EI, of course, are equal to x hat, y hat, z hat. Okay, Cartesian unit vectors. Right? Sorry. Okay. So in Cartesian coordinates, what is, for example, a del operator applied to, let's apply del squared. Del square operator is right in the Cartesian coordinates. And if we apply del square to E1 hat, let's say, which is basically del squared applied to X hat, what do you think the answer is? How would you evaluate it? Anybody? If you know the answer, you can just tell me the answer.
So del square x by del x square plus del square y by del x square, del square z by del z square.
Okay, so what is that? This is X hat, it's not X. Even if it was X, the derivative with respect to y for x would be 0, derivative with respect to z of x would be 0. So those two, the y and z terms would be gone, but the first order term would give you 0, right? But this is 0 for a completely different reason. Now think in terms of fields, right? See let's say there is a temperature field in this region, and here we actually have a vector field that is defined at all points in space, and at each point in space it has amplitude and a direction, right? That's why it's a vector, right? Now we're looking at X hat. So think about X hat as a field. Does X hat have, Anup, go ahead.
Yeah, in total it is 0, I think.
Okay, that's good. That's correct. It is 0, but it's not so much in total. It is 0 identically because of, let's think about X as a field, right? X hat as a field. I'm just going to think about this. And let's take this point here. What's the direction of X hat at that position? I mean, how would I draw the vector X hat at that position?
Towards the x direction.
Yeah, towards a positive X direction,
X-axis.
and it has unit amplitude. How about at this point over here?
It is 0.
At this point,
At that point, it is
1.
The same
yeah,
direction.
amplitude is 1 always. And what's the direction? This is my X direction. That is Y, and it's actually wrong. But let's take it that way, right? So I'm going to take my Z to be downwards here, just to be right-handed, just to have a right-handed system. Okay, so that's XY, and then Z goes down. And I was using my right hand for that. So at this point, what would be X hat?
The same direction.
Same direction. It should be exactly the same vector, right? So over here, exactly the same vector. Over here, exactly the same vector. Over here, exactly the same vector. That means all over that 3D space, X hat always has the same direction and same amplitude. Doesn't change. So then derivatives of it should be the special derivatives of it, which is gradient or divergence, or the del square. All of that should be identically 0, right? Everybody makes sense? Everybody with me? Same thing applies to y hat and z hat, right? So in Cartesian coordinates, the unit vectors are constant. They do not depend on the special position of any point, right? And so that's why when I apply this del squared, my job is easier. I only have to worry about the components of A, not the unit vectors. I don't have to differentiate those. They survive. I mean, they don't contribute anything. And so then I can take this E1 out, and then I will have del squared A1 plus E2 out, del squared A2 plus E3 out, del squared A3, which is now a summation I EI del squared of AI. Okay, everybody with me so far with that? And that's why I can make this jump, right? It's allowed, I am allowed to make that jump because, sorry, it doesn't look good. Because the del square applied to the unit vectors in the Cartesian coordinate is 0. Now, can you say the same thing? Okay, so this part is done. Can you say the same thing in the 3D spherical coordinates? So think about the 3D coordinates, and then we only specially care about the unit vectors. Now I'm going to be taking the X here, Y here, and Z there. Okay, so now, and I'm not going to look at now, let's say the, so let's take a look at 2 points, 1 point here. What is the direction of the radial unit vector r hat? We will try to look at all 3 of them. Phi hat. And let's take some extreme points, right? So I'm going to take, we use a different color here. I'm going to take point over here. Okay, the point along the z-axis. What's the direction of r hat? Anybody? Looking at this.
The Z direction.
Z direction, very good. So it's going to be upwards like this. That's r hat. What about a point here on the y-axis? What's direction of r hat there?
Y direction.
Y direction. Okay, very good. And naturally, of course, if you have some point on X, it's like that. So at any point, you join the line, join that point with the origin, and then it's radially away from that point. So r hat is like this. Okay. And over here, it's like that. So what can you say about r hat as a field? Is it constant everywhere?
No.
No, not constant. What can you say about phi? Would it be constant? By same logic, no. And so the unit vectors in any other coordinate system outside of the Cartesian coordinate system, they are not constant. They are fields. They themselves change, and that means del squared of r hat is now not equal to 0. Del square of theta hat is not equal to 0. Del square of phi hat is not equal to 0. So when you need to be very careful when we were doing this identity, del square A would be, if you wanted to express A in the 3D spherical coordinates, then it would be AR r hat plus A theta hat plus A phi hat, that is not equal to r hat del square of AR plus theta hat del square of A theta plus phi hat del square of A phi. These two things are not the same, right? You can't make that jump. And that means that vector identity that we saw earlier takes a completely different form. You can't write it like that. Okay, so how do we use that vector identity? You could still use it if you are being careful, right? And so you need to be very careful. And so let's take a look at this. So how do you make this useful, right? What you have to do is you need to calculate the components. Okay, so one needs to carefully evaluate gradient applied to ARR hat, gradient applied to A theta, theta hat, and the gradient applied to a phi hat. And once you have that, then you can apply another gradient to it. So that is something we're not going to go into, but we're going to take, look at a slightly different trick here. So what we are going to do is we can use alternatively we can use this identity let me label it. So not at this form, right? This is a tricky jump. At this stage, in the component form, at this stage, this identity is actually quite useful. So I'm going to put a box around it here. If it will let me do that. Okay, so this is useful immaterial of which coordinate system you're talking about, because you're not doing this weird derivatives of the unit vectors, right? So this is useful. This is more universal than the corresponding vector relation. So we're going to use that relation to actually define what we mean by the R component or theta component or phi component of del squared. So alternatively, we can use the identity, and let me label it identity. Let's call it I. That we just saw earlier, to define the components of del squared A. Okay. Either you do all this tricky and complicated business of taking the derivatives of R hat, theta hat, phi hat, that's time consuming. We could just use the previous identity. This is immaterial of the coordinate system. The rest of the quantities are, let's assume they're easy to evaluate. And so del squared A, which is the tricky one, we can simplify our work by just writing down. Let's say I want to know the phi component of del square A. That is simply going to be, okay, so let's take a look at this. Del square, I just need this part here. So I move it to the other side and then remove the triple curl or the double curl to the right hand side. Okay, so that's, I'm just going to get gradient with respect to phi, gradient with respect to phi applied to divergence of A. Remember, divergence of A is going to be immaterial of the coordinate system. That shouldn't change whether you evaluate it in the Cartesian coordinate system or in the cylindrical coordinate system or a 3D spherical coordinate system. that's a physically meaningful quantity. It just tells you how that vector is changing in space with the help of the scalar vector, scalar quantity. And so that is immaterial. This is independent of the coordinate system. Okay, does everybody understand that? So then this part is okay. That is coordinate dependent, but I'm only concerned about the phi component, so I can do that. Plus, curl of the double curl of A is also going to be a quantity that is independent of the coordinate system. It's just the property of the vector field. Does not matter which coordinate system you chose to express your vectors. So both of these quantities are going to be independent of the coordinate system, right? So I'm going to make a comment here. And you need to be very careful about all of these things. That's why we're spending so much time on illustrating this, because without that, this is field theory, right? So you need to understand some basic properties of fields and so on. And so you can also do del squared A R and del square A theta can be similarly defined. So how do you do this? These quantities, if you know the vector field, you can use Cartesian coordinate system to evaluate these independent quantities, the quantities that don't depend on the choice of coordinate system. And then you can apply del phi on it, on the first one, on the divergence, and take the phi component of that vector, double curl vector. And then you have the phi component of the del square A. Okay, does that make sense? Is everybody with me? You understand procedurally how you would do it, right? We saw two ways of doing it. First one is this tricky business of evaluating all of these individual quantities and then applying the del operator again. That's quite tricky because it's involves the derivatives of r, theta, and phi, and you don't want to worry about them too much. So can you express it in a slightly different manner? And here's a way to do it. These are easy to evaluate. If somebody gave you a vector field, you can evaluate these. Then all you have to do is take the phi component, take the phi derivative, and then you are done. You have a way to calculate the any component of del square A. Everybody with me? Okay. Now I asked you example 1.2 as a reading assignment. You have same issue in that example also. So you need to be very careful there. And so I'm adding another reading assignment here. So example 1.2 and equation and the equations 1.49 to 1.50 and the related discussion. Okay, so make sure you take these reading assignments seriously, because that is something that I will not be discussing in the class. It's for you to figure out, and it's just an extension of the discussion that we have had. So it's something you can manage and handle. The next item there, actually, let me add that also in here. So here's one, and another one is what the book calls it, application 1.1. Now this is application to quantum mechanics, but it's useful. It's about evaluating del cross L, which you will be using actually in your homework. So you will have to read that anyway for solving one of the problems on your homework. So I will let you look at that. Okay, so just time for a little break. Anybody has any questions at this point? Okay. If there are no questions, let's take a look at now derivatives. Of some simple functions. And in most cases, since we are dealing with fields, most of the functions that we are going to encounter in this class are going to be functions of position vector r and a distance vector r. Okay, everybody with me? And position vector r is given as r hat, where r is, if you wanted to express it in Cartesian coordinates, it would be, according to the Pythagoras theorem, x squared y squared z squared square root would be r, where x, y, z are the coordinates of, the Cartesian coordinates of that point that we're talking about. Everybody with me? Make sense? Let's take f of r is a scalar function of r. Then the derivative is simple. This is something you're familiar with. But when you're dealing with fields and r vectors, you are going to have various other interesting combinations. So you can have, for example, gradient of r. Remember I said r itself, which not the unit vector r, but the r as a scalar field, distance from the origin of any given point in space. That itself is a field, and you can calculate its gradient. What do you think that will be? Any thoughts on that? Some of these things I will do them for you. Some of these things you will have to figure out on your own. Okay. So gradient of r. Any thoughts? Anybody wants to do this? To tell me how you would do this? Okay, so you have to literally, yes, go ahead. Anybody has any
the
thoughts?
question is R a vector or a scalar?
R is a scalar, right? You cannot, so this is the first thing you need to remember. You cannot apply a gradient operator to a vector field like this, right? It has to be, because the gradient operator itself is a vector. So if you're applying it to vector, then it has to be either a dot product, which we call divergence. So don't ever forget the character of these operators. It's important. And if you apply to a vector field, another method is to take a cross product, which is called a curl of a vector, right? So if I'm writing it like this, that means r has to be a scalar. You can't, I would be wrong if I just write down r as a vector there. That this is this would be wrong. It has no meaning, right? It's a tensor operator, which, at least in the context of things that we're discussing right now, it has no meaning. So what would be this, right? So again, you can evaluate this. I'm not going to do it for you. I will just give you one little step here, right? So r vector, you can write down the r in terms of the Cartesian coordinates as
Square
x
root.
squared plus y squared plus z squared square root, and gradient operator is x hat. I will just make my life easier. Del x, y hat, del y, z hat, del z. So you can evaluate it, right? So I will let you evaluate that, and the answer turns out to be r hat. Okay, so this is going to be important. You kind of almost have to remember these very simple relations. Deriving them takes a little bit of a time. Here now r is a vector. So I'm taking r as a vector, and then I can evaluate the curl of it. What would be the curl of r? Anybody knows? It's now already, it's, you can think about this as a, well, R vector. If I were to draw a two-dimensional picture of it, it's actually radially away, going away from. So at this point, it's like this. At farther away points, it has higher and higher amplitude. The farther you go from the origin, the larger it gets, right? This vector, and so on, right? So you can imagine those radially coming out vectors in all different directions. So what would be the curl of this? Is there any curl? This kind of field has a divergence.
It will be 0, doctor.
0.
Is non-zero, and curl is 0, right? Curl means, how it rotates around. So it is going to be 0. And you can prove that, right? Again, the idea is the same. And then there are other identities that are there that are discussed in the book. I'm not going to write all of them, but I'm just kind of trying to help you develop intuition for some of these. Let's take now another function g, which is a function of the scalar quantity r, but the function itself is a vector. Okay. And c is a constant vector. Right? You can have a constant vector. You saw a example of a constant vector here. This one, for example, x hat in that situation was a constant vector. Its amplitude and the direction does not change as you go from one field point to the other. And so let's take a look at now a couple other identities related with this. When you have g as a vector quantity, you can either evaluate its divergence or you can evaluate its curl, right? Both of those are fair game. And so what you get in this case is divergence of g is you get g prime dotted with r hat, where g prime is basically just the derivative, right, of g. The curl of g happens to be r crossed with g prime. Okay, that's another interesting identity. Again, you have to take a look at this and try this out, right? So what is g prime? G prime of r is you take the vector of each component. So that's very easy. Is d over dr of g of r. Okay, that's what that is. And that means when you apply a divergence to a vector, you are eventually evaluating the derivative of g, but it's not the total derivative of g. It's only the r component that gets extracted when you're looking at the divergence. What's happening radially, right, in the direction of r. And when you are trying to look at the curl, it again is looking at the derivative g prime, but certain components of it that are perpendicular to that plane, right? If it's curling around, then the direction of the curl is always out and outside of that plane. If g, if g is lying in that plane, for example. Give me just a second here. Okay, so there are some of these interesting identities that have interesting interpretation. Let us take a look at one more. Now we have a combination. You can do combination like this. Gradient is an operator, but you can actually take the gradient dot product width of a g from the left side, and then it still stays in the operator form, and then you apply it to a vector, and you are going to get g back. Okay, so that's again very interesting identity. You can do something similar, just switch things around and then see what happens for the g. And this naturally has to be proportional to g prime, right? Because there is a derivative involved and it turns out to be r g prime. And I'm deliberately writing down all of the vectors, notations, vector on top of the symbols. The book uses boldface letters, so make sure you understand when you're reading these things carefully. Okay, all of these identities can be proven. You have to learn to use them. I will not be asking you to prove them in the exam. You will be asked to prove them in your homework, right? And so you need to be able to figure these things out based on their definitions. Let's write down one more interesting one. It turns out divergence of G crossed with R, right? So G is some field, some random field. You don't know what it is, right? You know, and it's just only thing that you know that it's a function of R. That means it has some specific value at R, and it does not depend on the angles. That means it's a radial field, right? If the angle changes, the value is not going to change. And this quantity, interestingly, is 0.
Excuse me, doctor, can we think of G like will be in the future like the electric field?
No, not really. I'm not saying anything yet, right? Because you can't make a general statement like that. The charge distribution is going to govern whether electric field is just the function of the radial coordinate. So this is a general function that is only function of R. Okay, it does not depend on theta and phi. You can't say that about, you can't make a general statement like that about electric field.
I see.
Okay,
Thank
so
you.
it's if you had a function of R alone, then these are the properties that it's going to have. We're just, for a field, the way you extract properties is being able to evaluate different sort of derivatives, and that's how you sort of figure out how it behaves, right? How it changes as you go from one space point to the next. And so I'm just listing some of the identities here that are interesting. They are by no means comprehensive list. I'm not copying everything from the book. You should be reading through the book for looking at these things. Okay, everybody with me? So this is just the functions of R. Now, interesting things is we normally almost always in E&M don't need functions of R. What we need is functions of R minus some other point R prime. Why? So let's just take a look at why. Okay, my goal is to find the electric field E as a function of R, let's say, due to some charge distribution that's sitting here. Okay, so that means naturally I'm going to need now two different coordinates, one that is expressing or keeps track of the charge distribution. So let's call it R prime, and the other one that keeps track of the position at which I'm trying to find the electric field. Does that make sense? So you have to keep track of two quantities, one that runs over the charge distribution or current distribution in the case of currents in the system, and the position coordinate, the point in space at which you are trying to determine either the electric field or the magnetic field. They are, we normally call them R. Okay, so you normally encounter functions of these. And so let's take a look at a couple of examples of that. Let's call, actually I shouldn't use that one. Capital R is the vector R minus R prime, right? And so, why R minus R prime? That's important to point out, right? So at each point, I'm going to now use a dashed line here, and let's use this color. So if the contribution to the electric field at point R from a charge that's situated at R prime, Coulomb's law depends on the distance, right? So it's going to be this quantity, the dashed line vector is what is going to be important. It's the distance between those 2 points, the source and the location at which you're trying to find a field. is what is important. And so I'm going to now remove this R here. R goes there. And this vector here is going to be R minus R prime. And it's this R minus R prime, that's the crucial quantity in electrostatics, magnetostatics, whenever you have sources. And so you need to be able to now evaluate functions of these and how they, so you get X hat plus Y minus Y prime, Y hat plus Z minus Z prime, Z hat. So that's simple. That is just the Cartesian representation of this. We're going to be able to write those things down in not just Cartesian representation, but also in the spherical and cylindrical coordinate system, as you will see later. If you take gradient of f of r, now we have a scalar r. It's going to be just like in this case here. Oh, I think I did not write this down, right? But you have this thing, derivative f prime of r. You can take similarly a gradient of r because it's a scalar quantity, fr. So you can do that, and that's going to look like this. If you have a let's say a vector function of r, so then divergence of g of r is going to be similar to the previous case, g of r, g prime of r dotted with r hat. So divergence only picks out how the function changes, right? The derivative, the special derivative in the radial direction, right? So this is, let's actually write some words so you see what is going on. Special derivative. And this whole quantity is the component of the special derivative in the radial direction. Now, in this case, the radial direction is has to be qualified because it's not radial from the origin. It's radial from the point where the source is sitting, okay? So make sure you understand that. So understanding what these quantities mean, you should reiterate in your mind. How do I verbally explain what's happening? That's going to be crucial for you to understand. So a divergence of any vector field which is a function of the distance coordinate alone, r alone, is component of the special derivative of that function, how it changes in space in the radial direction, right? So it only picks out because it's radial direction, that is divergence, right? So that's the kind of the physical meaning of it, but you can see that from here also. Similarly, the curl is going to be, again, G is the one that's vector, R is not, is going to be R hat. And this quantity will be non-zero only if G prime of R is perpendicular to R hat, right? That means the function has to change in such a way that it's not radially changing. It has to change in a direction, either in the theta direction or in the phi direction. And only then R crossed with that vector would be non-zero. Okay, does that make sense? So this is component of G prime of R perpendicular to both R hat and G prime vector itself. And so the curl is always perpendicular. It's coming out of the plane. If you are thinking about two-dimensional fields, the curl would be radially, it's not radially, sorry, it will be coming out of the plane of the board. And that's that. Okay, just for notational sake, when you have the gradient, I'm just going to define, and I think we wrote this earlier, del x and so on, right? I'm not going to write down the whole thing. We sometimes use del prime because now we have two coordinates, r and r prime. You may want to sometimes figure out how the charge itself is, charge distribution itself is changing. Sometimes it is useful to evaluate the del prime derivative or the gradient prime, which is x, the coordinate system doesn't change. So it's going to be x hat, but its derivative with respect to x prime, y hat derivative with respect to y prime, z hat derivative with respect to z prime. Okay, so just notation, remember that we will need that quite a bit. And let's say if you had a function of r and you want to take its derivative with respect to the prime coordinate, which is the gradient prime, that is going to be simply negative of the gradient with respect to f of r. And it's very easy to see that because r is r minus r prime always, and so the sign of r and r minus is always opposite, and so that's why you always have the negative sign or a negative relative sign here. Other than that, it's exactly the same thing. Everybody with me? So far? Okay, there is another quantity called convective derivative, which we're not going to need in this class. If we had the second part of the class, then we would need convective derivative, so I'm going to ignore that. Jacobian, I will let you read it on your own. Okay, so you need to read about coordinate transformation. So another reading assignment. And you need to learn about Jacobians for, I think, first problem from your book, from your first homework rather. This is 1.4.1 Jacobian determinant. It's very important when you do coordinate transformations. It's actually useful for any sort of orthogonal transformation, but here we are going to think about it in terms of the coordinate transformations. So I'm not going to go there. Let's take a look at now Taylor's expansion. It is theorist's biggest and most important tool, if you will, to figure things out, how they behave in the limit of some quantity getting smaller. So the scalar function, the scalar Taylor expansion you are all familiar with. Here it's going to get interesting because we're going to now bring in the operators, the gradient operators that we have just learned about. So f of x is going to be, x is a point in the vicinity of some other point where you already know the value of the function. So f of a, something that you know, then you can expand f of x around that f of a. And so x minus a df over dx evaluated at x equal to a plus 1 over 2 factorial x minus a squared. Let me actually move this over here. And then you have the second order derivative of f with respect to x. Again, it's a special value of that derivative that matters at x equal to a, and so on, right? So you can write that down. Next term would be 1 over 3 factorial x minus a cubed, third order derivative, and so on. And as you can see, if x is very close to a, the higher order powers, x minus a squared, x minus a cubed, they are all progressively smaller. And so you get a good approximation for it within the first two terms, right? The f of a and so on. So that's one form of the Taylor expansion. Don't ever forget that, because you need to know this so that you can simplify your work in some other context. Or if you want to write it down simply as x plus epsilon, and you know f of x, that actually makes things a little easier. That's 1 over 2 factorial epsilon squared d2 f dx squared, and so on. Here epsilon is going to 0 in the limit. Okay, that's that. Or we can actually use this form to simply look at it as an operator applying on being applied on f of x. I'm just going to write a couple of terms here. So first term, of course, is 1. The second term is epsilon d over dx. Third term is 1 over 2 factorial d2 over dx squared, and so on. And this is like an exponential operator. And so you could see exponent of epsilon d over dx applied to f of x. That's just a shorthand notation for the Taylor expansion. Again, those who took the math physics class, you have seen this, but now things get interesting. Everything is scalar. In ENM,
we need the epsilon squared in the second term. From in the
right,
second.
Yes. Yeah, very good observation. So what I'm going to write down that as, I actually just change it a little bit. Let me do this. I'm going to write it as epsilon d over dx squared, and so on. So then you could see the connection with the exponential function. Okay, so in general, in ENM, you have 3 things changing, right? We're talking about 3D space, and so you don't always have x plus epsilon. What you actually have is x plus epsilon x plus y. So you have functions of x, y, z, and then each one of them may be changing by a slightly different amount. Z plus epsilon z. In this case, how would you write down the Taylor expansion? Any thoughts anybody has? We're going to use this because that's our the compact notation always helps, expand things out or extend things to newer domains. And so we're going to use this. So instead of just f being just the function of x plus epsilon, you have x plus epsilon x, y plus epsilon y, and so on. So how about I do this? I apply epsilon x d over dx. That will take care of the Taylor expansion part for the x. Then I multiply by this. And then I multiply, of course. Then you can see it's a simple extension. Everybody kind of agrees with me? Do you see how that would be true? Right? Because both x, y, and z can change independently. So first you do the, let's say you do the z expansion first, then you do the y expansion, and then you do the x expansion. And the order shouldn't matter. Order is independent. Or you can now go into the vector notation where you have a function of r, but now you are adding another vector epsilon to it, and you want to try, the value of the function at position r. You want to use that to find its value at position r plus epsilon. And that is going to be very simply, because you have the exponential terms, exponent or product of exponents is the exponent of the sums. So I'm going to treat that as a sum, and you can see epsilon x d over dx, epsilon y d over dy is a dot product of epsilon and the derivative operator, right? The gradient operator. And so all of this, these 3 different terms that you have there, they add all together to take this form. Okay, everybody with me? And here epsilon, of course, is a vector. Everybody understands that, how all these 3 terms can be added together to take form like that. Right? Expand this out, and then you can see that it just matches with what you have there. And then you apply that to f of r. So very simple to write down the Taylor expansion in 3 dimensions. Right? Now you just use the gradient operator to be able to do that. And then you can expand. Once you have that exponential form, you can always expand it. And you can see that the first term is going to be epsilon times the gradient. The second term is going to be epsilon dotted with the gradient operator squared, and so on, applied to f of r. Everybody with me so far? Does that make sense? So that allows you to expand or extend gradients, not just in 3 special dimensions, special 3D space, but if you need to have functions of higher dimensional vectors, right? You in linear algebra, you understand that vectors are not just 3D special vectors. You can have many dimensions, and you can have gradients of them, or all of those vectors, all of those components. Let's say you have 10 different components. All of them are changing at the same time. You can address that with the help of the same idea. Same idea would work there. And one of the prominent modern example of this is the so-called machine learning. When you're trying to evaluate how a certain quantity, let's say the life, the age of humans, right? You want to determine how the age of humans depends on what sort of parameters. You can start parameterizing, where they were born, which year they were born, their age, their lifestyle, their diet, so there are a multitude of variables that you could think of them or treat them as these vectors, input vectors. And then how all of the mathematical machinery works is basically through these kinds of gradient operators. Okay, so gradient operators are very, very useful and common. And you can understand that mathematical machinery very, very simply, just with the help of the understanding that you have. Now we just have a minute. So I'm going to quickly state the divergence theorem and the Stokes theorem. And these are now integration of vector fields. So far, we have been worrying about the derivatives of the vector field. And the divergence theorem says if you take a volume integral of a divergence of a certain vector field, then that is equivalent to the flux of the field passing through a surface. So this is an enclosed volume. So you have a certain volume. Let me just draw it kind of randomly. It shouldn't have a kink. So that's my volume inside, and the boundary is the surface, right? So think about this as a 3-dimensional thing. So it has a volume and it has outer surface. And so ds is the unit vector of that surface pointed away from the volume, and f dot ds would just give you how much of that field is coming out of that. So actually ds is normally written as ds dotted with n hat, and n hat is always away from the volume. Okay, so that's how that works. That's the simplest form. We will take a look at that in more details later. And then I want to show you I want to write down the Stokes theorem, and we will take a look at their properties in the next class. But you need this so that you can start working on your homework. So Stokes theorem is now, of course, naturally, it's going to be related to the vector quantity, which is the curl of f. Now, because it's a vector quantity, to make sense of it inside an integral, you need to have a dot product of it with some vector quantity, which is now the normal to the volume. right? And this is the only combination you're going to have that is meaningful. Yeah, no other, because the integrand should be a scalar quantity always, right? You can't have a vector and you do integral of that. That does not make sense. That's a meaningless stuff. And so this, then if you have a surface, right, this one as a volume, I should probably shade this, right? So okay, so that's a volume. Okay. And the surface is this, and it would have a boundary, a contour. And so this becomes a contour integral along the length of the contour. And you take a dot product of the small length element along here, dotted with the field. Okay, that's Stokes' theorem. You have seen these things before. You are just going to understand and use them, understand them deeply, and use them more efficiently from here onwards. So that's it for now.